Good afternoon. My name is Ioana Delaney. Gia and I are software engineers at IBM Spark Technology Center. This is us. We are located in San Francisco, and one of our main goals is to contribute to the maturity of Apache Spark. Spark applications often have to directly query data sources external to Spark, such as relational databases and files. For that, Spark provides a data source API, a mechanism for accessing structured data through Spark SQL. This API supports optimizations such as filter pushdown and column pruning, which, depending on the data source, they only provide a subset of the functionality that can be pushed at the data source. This work extends data source API with join pushdown. Join pushdown is nothing more than selection and projection pushdown, which are already supported by Spark. With small amount of changes, this work significantly improves query performance by reducing the amount of data transfer and exploiting the capabilities of the data source, such as index access. What are data source API? They are a simple mechanism for accessing external data sources. Spark provides built-in libraries based on the API, such as Hive, Parquet, JSON, JDBC, and also external third-party libraries. Using this API, user can read and save data through generic load and save function, or through relational SQL tables, which are data frames with persistent metadata and names. At the same time, developers can build new library based on data source API. For example, to create a new data source, one only needs to specify the schema and how to get the data. An important characteristic of these APIs is that they are tightly integrated with the optimizer, with Spark Catalyst, by allowing optimization to be pushed down to the data source. These APIs are used by any Spark application that operates on data coming from external disparate data sources. Next, I will show some examples. A first example, it's an enterprise-wide data pipeline that connects data throughout an organization. For example, Spark Framework, in this example, Spark Framework extracts the records from the data source, possible applying some predicate. It caches the data frame results and performs the join locally in Spark with the updates coming from the stream. An example of data pipeline we have at Bloomberg, as they presented their architecture at Spark Summit 2016. Another example is SQL acceleration with Spark to enhance a SQL engine with Spark capability, Spark Analytics. Some vendors overlay their database cluster nodes with local Spark executor processes. The data frames in Spark are derived from the existing data partitions of the data source cluster. In addition to enhanced SQL capabilities, the collocation of the data executors with the database engine processes will minimize the latency of accessing the data. IBM-DB and other vendors provide SQL acceleration through collocation or other forms of integrated, Spark integrated architecture. And probably the most common example is ETL from legacy data sources. Data from relational databases and files, it's offloaded into Hadoop or other data sources. All these API show that Spark is very often used to operate on external data sources. It ingests the data from the different sources and performs fast in-memory analytics on their combined data. It supports both structured and unstructured data, and it applies analytics everywhere without the need of data centralization. As with any federated system, there are challenges when querying external data sources. One is network speed. For example, we have two large tables, a very selective join applied between two large tables. The tables reside in a relational database. Spark reads the data and performs the join locally. Instead, if the join is pushed down to the data source, the amount of data will be significantly reduced and the query will run many times faster. Another challenge is to exploit the data source capabilities. For example, the indexes define on the tables that reside in a relational database. In this example, the database has an index on a larger table. The join execution in Spark approximates the time to read the larger table. In DB, which is our underlying database, the time to execute a join is the time to scan the smaller table and probe the index. If the join is pushed down to the data source, not only that we reduce the amount of data transfer, but we also take advantage of the presence of the indexes of the data source. And our query runs 100 times faster. Therefore, we consider join pushdown as an alternative execution strategy in Spark. Join pushdown is nothing more than selection and projection pushdown. It is another means for performing selection pushdown. Similar to selection pushdown, it may reduce the amount of data transfer, but it also provides Spark with the capabilities or the functions of the underlying data source. With small API changes, we got a very significant performance improvement. Probably the most significant concern about data federation is acceptable performance. Optimizer is the component that decides the best way to execute a query. It is the one that chooses the implementation for various relational operators and their order of execution. In a federated system, the optimizer must also decide where to execute, if to execute an operation on the federated server, Spark in this case, or at the remote data source. For that, it needs knowledge of what each data source can do and how much it costs. For example, if the data source is a file system, it would not make sense to assume it's smart and ask it to perform complex operation. On the other hand, if the data source is a relational database, it might be a good idea to take advantage of its power if it will reduce the amount of data transferred back to Spark. Today, Spark Optimizer Catalyst uses a combination of heuristic and cost model. Cost model, it's an evolving feature in Spark. So until federated cost model is fully implemented, it might make sense to use some safe heuristics. Next, I will talk about some of these heuristics. One is to minimize the amount of data transfer. On this slide, we have two queries, each reading data from a relational database using JDBC data source. JDBC is Spark built-in data source API to connect to relational databases. On the left-hand side, we have an example. We have a join among three tables, store, sales, date, and store. It is an example of a filtering join. A filtering join will reduce the number of rows after the join. On the right-hand side, we have an example of expanding join. An expanding join may increase the number of rows after the join. In this example, we slightly change the previous query and add the fourth table, store returns. From the query execution plan, we observe that this join applied at the end will increase the number of rows from 25,000 to 95,000. Below, at the bottom of the slide, we have the two table diagrams that shows the relationship among the tables. In case of a filtering predicate, we observe a one-to-one join among the store sales and the other table. That means that the join will match a row from the store cell with at most one row from the other tables. In the case of an expanding join, the table diagram shows an M to N relationship between store sales and store return, which means that a row from store sale might match more than one row from the store return. In the case of a filtering predicate based on a one-to-one relationship between the table, it is provable that this join will not return more rows than the end side of the join, the store sale table in this case. This relationship among the table is characteristic to a certain type of join, frequently used in data warehouses and called star joins. A star join is a join among tables in a star-schema relationship. Star-schema is the simplest form of a data warehouse schema. It consists of a fact table referencing a number of dimension table. The fact table contains the main data or the measurement about the business, and the dimension table, usually smaller table, describe the characteristic or the dimensions of a table. Fact and dimension table are in a primary key foreign key relationship. Here I show part of the store cell fact table diagram of the TPC-DS benchmark, which is a proxy of a real data warehouse. The fact table store sales, it's at the center. The diagram looks like a star with the store sales at the center. Surrounding the fact table store cell, there are the dimension table, which are related to the fact tables through one-to-one joins. Because of the primary key foreign key relationship, star joins are considered filtering join. They can simply be viewed as filter applied to the fact table. Because of that, they are safe to be pushed down to the data source since they will not increase the number of rows. Today, Catalyst recognize star-schema join, and we use this information to detect and push down star join to the data source. Another heuristic is to maximize the amount of functionality that can be pushed down to the data source. Here we have an example of a five-way join with some data coming from a relational database using JDBC API and some other tables defined on HDFS in Parquet file. The default join ordering in Spark might mix the table from the two data sources. To maximize the operations that are pushed down, we extend the join enumeration in Catalyst to reorder the join based on the data source. In the logical planning optimization phase, we detect tables which belong to one data source and join them together. Then during the physical planning strategies, we might choose to push down the join and replace it with a scan over their result. Join reordering based on the data source is an important alternative execution plan for global federated optimization. Next, I will talk about how to achieve parallelism when complex operations such as joins are pushed down. In Spark, partitions are the basic unit of parallelism. For example, JDBC uses the following option to partition the table read of the data: partition column, lower and upper bound, a number of partition. The number of partition dictates the number of tasks to be launched. The lower bound and upper bound, the parameter decide on the partition stride. With this option, Spark will split the table read across executor. In this example, we have a join between two tables. Both are partitioned on the join columns. Internally, Spark will generate a SQL statement to fetch the data. Each SQL statement will fetch a partition of the data. Spark will open dedicated JDBC connections to fetch each partition. With this execution model, the operations above the scan over the JDBC relation will be parallelized. How to partition when joins are pushed down? One way is to push down partition collocated joins to the data source. A collocated joins occurs locally on the database partition on which the data resides. An example will be when the partitioning in Spark aligns with the data source partitioning. This execution model works best for those Spark architecture that have the Spark executor connecting to each database node and retrieve the data directly. However, collocation, it's hard to be achieved for multi-way joins, and in general, issuing multiple concurrent SQL statements with complex operation might impact the performance of the data source. Therefore, this form of partitioning should be done based on the cost. An alternative design is to perform partitioning in Spark by choosing the best join method that favors parallelism. We know that broadcast hash join is the preferred method when one of the table is small. The small table is broadcast to each of the nodes of the larger table. The parallelism of the larger table will be maintained, and shuffle is not necessary. However, if the large table comes from a single partition JDBC connection, the execution will be serialized on that single partition. The Spark query will be serialized until some other operator above will do the repartition. In such cases, shuffle hash join and store merge join may outperform broadcast hash join because of the lack of parallelism in the latter. Here are some of our performance results. We use 1 terabyte TPC-DS benchmark, which is a proxy of a real data warehouse. The underlying business model, it's a retail product supplier. The benchmark applies a variety of queries from ad hoc to reporting to data mining. For our testing, we use a mix of 2 data sources. Part of the benchmark data is stored in an IBM DB2 database, which connects to Spark using JDBC data source, and part of it is in a Parquet file. From this table, we observed that we got a good performance improvement, up to 30 times improvement. Next, I will present the data source API for reading the data. The APIs are relatively simple. To create a new data source, one needs to provide a schema and how to get the data. A base relation, which you will need to define a new type of base relation, which is an abstraction of a collection of tuple read from the data source. It provides the schema of the data. Then you need to specify how to get the data. For that, there are several traits. One trait, the simplest one, is table scan, which reads all the data from the data source. Spark will process the remaining operations. Then, if the data source knows how to do things like eliminate a needed column, you can use the prune scan interface. Spark will provide the columns that needs to be retrieved. The prune filter scan should be used with those data sources that knows how to apply predicates. And then we introduce a new API called push-down scan for those data sources that know how to apply complex operations such as join. Push-down scan, it's a trait of a base relation. It extends the prune filter scan with data source capabilities. There are 2 methods that needs to be overwritten: the build scan, which take as an input a set of projected columns, the predicates to be applied, including the join predicates, and the set of columns, the set of tables to be joined. It returns an RDD of rows. And then the other method, it's get data source, which is mainly used by Spark Catalyst and other planning strategies to determine the data source to which table belongs. Then we also introduce a data source capability trait to model data source characteristic, for example, the type of supported joins. And lastly, a few words about our future work. Our goal is to transform Catalyst into a global optimizer. A global optimizer will generate an optimal execution plan across all data sources. An operation can be executed in Spark or executed at the remote data source, depending on the cost of executing that operation and the cost to transfer data between Spark and the data source. The key factors that affect global optimizations are remote table statistics, such as the number of rows, number of distinct values, and the data source characteristics, such as CPU speed, I/O rate, and network speed. Our work will extend the data source API with data source characteristic. We'll retrieve and compute data source table statistic and save them in the Spark global catalog. We will define new cost formula and integrate them into Catalyst data source cost model. And that was it. Thank you.
Thank you. Thank you, Ioana, for the wonderful presentation. We have about 9 minutes, lots of time. There are 2 mics on either side of the camera. Feel free to walk up to it and fire away. Any questions? Yeah, do you mind walking up to the mic, because we're recording and we really want to catch it on the audio. Thank you.
So the first question. Thank you for the talk. Well, it was really interesting. And the question is, are you going to open source this extension, so put it into the Spark OSS, or it's your own internal hack?
So currently we have an internal prototype for our product, but our goal is, yes, to try to push it into Spark.
Any other question? Going once, twice?
Okay.
Go ahead.
One more question. Well, actually, do you think to use it, to do it clearly with strategies, by not introducing a hack to the Spark OSS, but doing through the strategies?
Sorry, just a bit. So if I think if Catalyst is a
Catalyst has a set of strategies that do all the decision, and they have an extended point, so you can extend, add your own strategies.
Oh, you're talking about you want to extend the Catalyst cost optimizer to putting on your strategy?
Yeah, well, the question was why you don't use just the strategies, but extend extend API.
Extend the API. So
I think what she's asking is, why don't you actually extend the CBO to extend the own operator rather than writing your own?
I think both needs to be done eventually. So for example, the join reordering happens in the logical cost optimizer. So we extend their join enumeration rule to recognize data source, and we reorder the join. And during the planning strategies, we are choosing the best join method. For example, if we detect a star join, we will heuristically decide to replace that join with a scan. If it's not a star join, that will let the Spark strategies to just go ahead with the default planning. In the future, yes, we will need, the cost-based model will definitely be integrated into the Catalyst itself, but the Spark strategy is also, that's the physical planning, so either based on cost or other heuristic, but both will have to change. Yeah. So.
Thank you.
If there are no questions, please give a warm welcome to. Oh, there's one more. Thank you.
Yeah. So is this the work you've done? Is this very specific to making use of other data sources, or is it also something just making enabling faster execution in general?
No, yeah, this is targeted mostly for relational data sources to basically take advantage of indexes, other more sophisticated join methods that they have. Without, similar to filter push down. Also, the filter push down, the goal is to reduce the amount of data transfer, and we observed an extremely high performance improvement. So obvious join push down, it's another way to reduce the data transfer. And for any data sources that knows how to implement joins or other, it's...
And just to expand on that, I think one of the primary reasons why the CBU actually pushes these down high-level operations is because if you're dealing with very large, high-performance databases, they are primed, they're actually tuned, they're written by people who can actually optimize their code. So instead of Spark doing all the optimization for you, I'm going to say, go and push it down to the data sources so they can do efficiently. They can use primary indexes, they can use secondary indexes, they can do all kinds of things that people have spent their entire life writing PhDs to make those very optimal. And so if they can actually get less data for you, this less data comes up and Spark can run a lot faster. And that's what I think Ioana was trying to tell, is that we'll have to push down as much as work we can do. So Spark does less work, you write less code, and everybody's happy. Well, give a big hand to Ioana, please.
Thank you.